Good afternoon, everyone. Welcome to the second session of quantum computing. I always start the lecture with a brief revision of the previous week, so we'll do that, and then we'll continue with the next chapter. So last week in the introductory session, we actually wondered how you can speed up an algorithm. We've discussed different approaches, like profilers, using a different implementation, parallelization, and improving the complexity. And that's what this course is about. We will use parallelization, massive parallelization in quantum computers in order to improve the complexity class of certain problems. That's the goal. We looked at a motivation, which is the Grover's algorithm or quantum search. We saw a problem that would really look like O of n in traditional computing, which is in fact then an omega of n. We cannot do faster than n, but with a quantum computer, we can do this in the square root of n, so we get a squared speed up. That's one algorithm we will discuss in a few weeks' time. We looked at quantum computers, in particular some of the offerings of D-Wave. We discussed the organization of this class, and I'll provide more information on this whole presentation and marking thing later in a few weeks' time, because first we need to advance with the foundations. And you had some time to also do further background readings, like this chapter on quantum technologies, which can give you a little bit of a preview for the coming weeks. So I'm curious, has anyone read this chapter? If you have, maybe a green sticker, or read. If you have not, as usual, probably there will not be many positive reactions, but you should definitely read this because it will give you a better understanding. Horst Kuhnhardt will also talk a little bit about his history of quantum computing, some applications, business potentials, and some of his views. He will present this next week. So next week I'll be away, but I will open the Zoom session at 2 p.m. at the same time. And then Horst Kuhnhardt will become the host of the Zoom session and will record it in the cloud. And I'll sign out then and go to my meeting, but he will teach everything next week and discuss those topics. Last week, we also looked at foundations that we need for this course. We looked at complex numbers, what they are about, and why they are so helpful for quantum computing, and looked at a couple of concepts that are key to this course. We briefly revised them. And we also looked at linear algebra, such as vectors, vector spaces, matrices. We did a quick revision of some of those concepts. And then we saw we can not only plug real numbers in there, we can also plug complex numbers in that. And then we talk about complex vector spaces or complex linear algebra. Most of those things just behave the same, like you can add two vectors of complex numbers, or multiply matrices of complex numbers. That doesn't change. You just have the real and the imaginary part. Some things are slightly different, like eigenvalues, eigenvectors, but we don't need to do that from scratch in this course. However, there are some important new concepts that we will need, like the conjugate matrix, the adjoint matrix, and unitary matrices, which we discussed, which is something we will also be using as of the chapter we're using now, or that we will start discussing now. The tensor product is another crucial concept. So we can assemble two vector spaces, and that's also something we will need in the coming chapter now. So you are also most welcome to take a look at the Janowski and Manucci book, which is the Quantum Computing for Computer Scientists book. All of you have an opportunity to access it. You don't need to buy it. And today, we have the goal of getting a little bit closer to quantum theory, but we will not be able to directly have a head start with quantum theory because this course is not for physicists. This course is for computer scientists. And later, we not just want to do the quantum theory, we actually want to look at the architecture of quantum computers and how we can, or which operations we can use. And we will try to describe all of this in terms of linear algebra. And that's why we will today apply linear algebra to describe systems. Once we have done that, we will also already in this chapter look a little bit into quantum systems, which we will then elaborate on in chapter 4 in a few weeks. And then we have everything to actually start building quantum computers or use the fundamental operations. So we need to look into systems, quantum theory, and then we can actually dive into computing. So we have 2 more chapters, which are foundations or preliminaries in order to actually do proper quantum computing. And today, we will concretely look into deterministic systems. The deterministic systems are just something we will establish in order to look at a mechanism that we will use to describe those systems in terms of vectors and matrices that is not related to quantum computing yet. However, we start to establish a formalism that we will need in quantum computing later. So these deterministic systems are just the beginning. Once we have them, we want to advance them by thinking in terms of probabilistic systems, which is again not quantum computing yet. It's just one extra step of complexity. And then once we have described probabilistic systems using matrices and vectors, we can actually then again make that mechanism slightly more complex and describe quantum systems. And then we're getting closer to quantum computing. And then we have a mechanism that would actually only work for 1 qubit, 1 quantum bit. And then we will advance this and see how we could actually later establish a formalism to look into multiple qubits at the same time. And for that, we need to assemble systems, and that's where we need a tensor product. So the first 3 steps is linear algebra, initially just with real numbers in the first 2 parts, then with complex numbers, and then we need a tensor product. So in this chapter, we essentially need almost all of these math foundations from the previous chapter. So that's the outlook. And I'm curious if you have any questions about what we did last week. If you have a question, maybe just raise your hand here in Zoom and turn on your microphone. You can also just send a question here in the chat. I'll be most happy to answer your questions. Maybe just raise your hand if I shall wait for you, if you're typing your question, or if you need some time to set up your microphone, whatever. But since there are no hands raised, I assume there are no questions. Today, I will always show some slides, and then we will also do some calculations on the whiteboard together. So this will be also a more interactive part, and from time to time, there will also be some assignments for you that you can quickly try out, and we can discuss the solutions. So I said our goal for today is that we can start to describe quantum systems from a purely mathematical way without actually understanding from a physical perspective what quantum systems are. That's something that would be the next chapter, quantum theory. We will today establish a mathematical mechanism, and all we do will be about graphs and matrices. So a graph is a very fundamental data structure in computer science that all of you should know, and we will use matrices in order to describe what these graphs do. And later we will use complex numbers in order to do this for quantum systems. But we will start with a deterministic system just to establish that mechanism. So we have the following figure here And what this does is we have 6 positions. We have positions 0, 1, 2, 3, 4, and 5. And each position has a number of marbles. So a marble is just a quantity we can store in each position. And what is denoted here is a concrete state, because we have 6 positions, and in each positions we have some concrete values, which are for now integers, and they are integers 0 and greater. And we can describe this state in this graphical way. So we write the numbers, 6 marbles are here, 2 marbles are there, 1 marble is there. However, we can also describe this as a vector. So we will use throughout this whole course, we will always use vectors to denote states. And usually we will always use column vectors, but just in order to write this in one line, and I need less space, I use a row vector. And this row vector is then 6, 2, 1, 5, 3, 10, which are just the values from position 0, 1, 2, 3, 4, 5. So 6, 2, 1, 5, 3, and 10. And we just use this row vector for that we need less space in the vertical, but usually we always denote our states as column vectors. That's why I can turn a row vector into a column vector by just transposing it. So you know how to transpose a matrix, and similarly, we can transpose also a vector. That's our system we have for now. And there's always a lot of text in here in the slides, which also helps you for the revision. So I will not read it out, but you're most welcome to read it later for revision. And what I now want to do is I want to describe dynamics in this system. Concretely, I put in arrows or edges, and they describe how these marbles move in one time step. So we will think in terms of discrete time steps, and we have our system, and we will evolve that state into a next state by moving around these marbles from one time step to the next time step. And if we go ahead one time step, so from our current state to the next state, we will move all the marbles from position 0 into position 5. So this edge means move all the marbles in one time step to here. From position 1, we will move all the marbles in position 2. The ones from position 2, they will be moved to position 4. From position 4, we will move them to position 5. And from position 5, we will move them to position 2. And everything that is in our position 3 will just stay where it is. So we have a cycle here. I will now visualize this also for you on the iPad, which I will just open in a moment. Just wait a second. So I will visualize the system we had just used, and then we will try to describe the dynamics as a matrix. So we have the position 0. I'll just change the color. We have our position 0. We have the position 1. We have position 2, 3, 4, and 5. And we said we have 6 marbles in here. We have 2 marbles there. And we have 1 marble here. We have 5 marbles in position 3. We'll have 3 positions in marble 4. And we'll have 10 marbles in position 5. And we said the dynamics look the following. I can also use a different color just to highlight this. So that's what we just discussed in the slide. And we can now think about if we can represent these dynamics as a matrix. And before we also said that this state can be written as a vector. We use this row vector, but we can also now write it out properly as a column vector. So this was a 6, 2, 1, 5, 3, oops, and 10. And we will now describe our matrix in order to transform our state into the next state, so the next so-called time click. And that matrix will be called M. And the matrix will have 6 rows. So we will have something in the first row that we will denote in a moment, then something in the second row, and so forth. So we need 6 rows in the matrix to describe each position, how it will eventually, or what it will have evolved to. So a matrix with 6 rows, and it's also in fact 6 columns. And I will show you now how we can describe those dynamics as a matrix. What we see is we move all the marbles away from position 0. And position 0 has no incoming edges. So if we do one time click, everything in position 0 is gone, and there are no marbles coming in from the other positions. So we will just write 6 zeros in here, because this one here would describe, so this 0 would describe what position 0 gets from position 0, but it's all gone. The next one would describe, again, position 0, but what it gets from position 1. The next 0 is, again, what position 0 gets from position 2. But position 0 doesn't get anything, so all these elements are 0. It's the same with position 1. It only has an outgoing edge, but nothing is coming in position 1. So it's also just zeros. Position 2 gets something. So we'll look into position 2. Position 2 has an incoming edge from position 1 and from position 5. So what that means is, if something goes from position 1 into position 2, we put a 1 here, and position 2 has also an incoming edge from position 5. So we also put a 1 here. And all the other values are 0, because the position 2, which is this row, gets something from position 1 and position 5. Is that clear to all of you so far, how we denote this mechanism? Maybe a thumbs up or some negative sticker if it's not clear yet. But I think so far it's straightforward. Now, maybe without looking into the slides, maybe you can send me in the chat what the next row would look like. And the next row would be the row for position 3, which has this cycle. So it has incoming from its own position. So maybe you would just send me the values of the next row here in the chat of what it would look like. And most of the submissions are correct. There's a little bit of a confusion, but most of them look fine. First of all, there's a 0, 0, so 3 zeros, because position 3 doesn't get anything from position 0, 1, and 2. But position 3 gets something from position 3. So this would be this one here. So I put a 1 here just to highlight this. And it has no other incoming edges. So we put 2 more zeros. Position 4 only gets something from position 2. So we put a 1 here because position 4 only gets something from 2, nothing from 0, nothing from 1, and nothing from the others. Now the last row is position 5, which gets something from position 0 and position 4. Maybe you can also send me what that row would look like. And we got multiple responses. I think sometimes there's a typo or something from what you sent. So position 5 gets something from position 0. So there's this 1 for this first edge. And position 5 gets something from position 4, which is this one. And all the others are 0. So that's what the matrix would look like that describes this dynamics. So we always put a 1 in an element if there's a corresponding edge. Otherwise, we put in a 0. And remember, the rows describe the target and the column describe the source where it would come from. And now we can try something. We have our matrix M, and we have our vector X, and we can now say, well, first of all, I call this matrix M, but I just removed the M here because I don't want to copy and paste the matrix. I want to directly start with a calculation. We have our matrix M, and I want to multiply it with X. And X is this vector from before, which was 6, 2, 1, 5, 3, and 10. So I multiply the matrix M, which we had before, and from the right, it's very important that I multiply my column vector from the right, X. If I multiply those two, then I'm actually denoting what happens in one time step. So I have my state and I apply this dynamics once, and I move ahead one time click, and my state will evolve. We can try this out, what it would look like. The result we can call, for example, Y, which is the next state. So we multiply the column with the matrix. Since the first row of the matrix are all zeros, this would also be 0. Then the second row of the matrix is also all zeros, so the multiplication would also lead to a 0. Then we can look into the first row, the third row, which I'm just looking for a color. We have this 1 here and the 1 here, so this would address the 2 and the 10. So it's 2 times 1 plus 10 times 1. So it's 10 plus 2, which is 12. So we would then have 12 marbles in position 2, no marbles in position 0 and 1. You can now continue this for the next 3 rows and send the values that the next 3 rows would have, maybe without looking into the slides, and then we can see what the next state is. So we got a few suggestions. It's a 5 because we have the 5 here and the corresponding 1 here. Then we have this 3, and we have the sorry, I just got lost. We have this one here. Yeah, so this would be then 1. This one, 1 times 1. And the last one here would be a 6 plus a 3, which is 9. So what we have just described is we have the dynamics represented as a matrix. We would then multiply from the right our column vector, and we have a new state, which is just 1 time click later. And we call that state Y. If you look into the slides, there are a few more explanations, but just for what I have said so far, how you can turn these edges in the graph into ones and zeros in our matrix. So feel free to read the slides for revision, which is definitely helpful for you, or if you so far got the explanations, that's good. There is something that you may notice. There is a requirement, because it's a deterministic system, and the deterministic system comes with a requirement that means that each position in here, so position 0, 1, 2, 3, 4, and 5, that they have at the most one outgoing edge. In fact, it's always one outgoing edge, but it could be a cycle, so it just stays. But a position cannot have 2 or 3 or more outgoing edges, because that would be not deterministic anymore. Then it would be probabilistic where it goes. So this is the requirement, that we have exactly one outgoing edge, whereas outgoing edge could also be the cycle. So the elements or marbles, they just stay. What we can also think about is we can have now a matrix that represents 2 time clicks. So we have done 1 time click, but we could also have multiple time clicks. And there was a question here. There's a question in the chat which says, what happens when 2 nodes have arrows to each other? So you sort of mean that there is one arrow going from one node to the other, and there is an arrow or edge coming back from that second one to the first one. Is that what you mean? Maybe just confirm in the chat. So that would mean that they are just swapping. So we could sort of visualize this here. We have a position 0 and a position 1. So we have 5 marbles here and 6 marbles there. So you mean something like this. So they would just be swapping in a time click. And if you do 2 time clicks, you would just be back to the original one. But this is just an extra note. Now, I hope the answer helped. And now we want to know what will happen 1 time click later. So we have done 1 time click, and now we want to do another time click and evolve the system again. So what we could do is we first have our x, which we multiply from the right to m, which is then y. And then one more transition would be we take our y, which is our new state, and multiply it again with m from the right. And this would be, for example, called z. So we have 2 transitions. This is something you could do step by step. So first you multiply x from the right with m. And then again, your new y, you multiply from the right with m in order to get z. But that looks quite boring. And what you can do, in fact, is you can come up with a new matrix, which we call m squared. And m squared is m times m. So we multiply m with m, so the matrix m with itself, which gives us a new matrix. And then we have this matrix m2, and then we can just multiply our vector x from the right in order to do two transitions implicitly, because m squared does two transitions, so I don't need to first multiply x with m in order to get y, and then again y with m. So I can just come up with my matrix m squared, which you know how to do. You just multiply m with m, and then you have a matrix that does two transitions. We can look at that now in the slides. I have formalized this in the slides, and I say in the slides, we have this matrix m squared and the element ij, so the ith row and the jth column, that's one if there is a path of length 2 from j to I, meaning we do two steps is possible, and then we would have a 1. But looking at that step by step is quite bothering. So we rather just do our matrix multiplications. We have m from before, the one we saw in the slides. And I can have m squared, which is matrix m by matrix m. And we finally get this matrix. How to multiply matrices, you know that. Feel free to double check if the matrix is correct. I have done all of this when I created the slides. But now if we do very lengthy matrix multiplications on the iPad, it would just take a long time, and most likely we'll just have some error. Feel free to try this out at home to multiply this matrix with itself. The answer should look something like this. And then I can simply multiply my vector x from the right with m squared in order to do two transitions. Are you all okay with this deterministic approach so far? What the matrix should look like and how to multiply an element with the matrix? Maybe a thumbs up or green sticker if this looks reasonable to you, or a red sticker or questions if there are any doubts. So far, again, has nothing to do with quantum computing. We have just established how to transform a state into a new state. And we've done this purely deterministic. And now we will make it more complex, and we will work with probabilistic systems, which are one step towards quantum systems. When we now model probabilistic systems, we don't think anymore in terms of multiple marbles. We will only think about that there is one marble in the system, and that marble is somewhere at some position, but we don't know exactly where the marble is. We only know probabilities in each position. So how likely it is that that one single marble is in that position. And we will now represent our state in terms of probabilities. So it's just a single marble, and we have probabilities of where that marble could be. This is now a smaller system, just with 3 positions or 3 entries, and our state x could look something like 1/5, 3/10, and a half. And these 3 values, they add up to 1 because it's 0.2, 0.3, and 0.5. So they have to add up to 1. That's a requirement for the probabilistic system, that all these probabilities in the state add up exactly to 1. So there's, for example, a 1/5 chance that the marble is in position 0, or a 50% chance that the marble is in position 2. And we can also do this on the iPad and look at the next system and how it evolves. I'm just switching back to the whiteboard, and we can directly develop the system. Now it's probabilistic systems. And just to keep it reasonable, we use somewhat smaller systems now with, for example, 3 positions. So we have position 0, position 1, and 2. And we can say there is a 1/3 probability to move from position 0 to position 1. So now we use also probabilities to describe these transitions. We can say there is a 2/3 probability to move the marble from position 0 to 2. We will later see how these probabilities need to add up, but for now we just build one example system, and then later we will look into the underlying constraints that are necessary. But the marble is in position 0, and it will either stay in position 0 or it will go to position 1 or position 2. Since it cannot stay in position 0, there's no cycle, it has to go to 1 or 2. So there's a 1/3 chance and a 2/3 chance, and they add up to 1. If we are in position 1, there is in fact a 50% chance that the marble stays in position 1. There is a 1/3 chance it goes from 1 to 2. So what's left is 1/6, and that's that it goes from 1 to 0. Now we need to think about how the marble can move from position 2, and we could, for example, say there is a 1/6 chance the marble moves from 2 to 1. So if it cannot stay in 2, then it would also go to 0, and that is then a 5/6 chance. And this is our probabilistic graph, and I'm asking you now, or we'll start with the first row. We have our matrix M, and we want to describe these transitions. It's again, we use a row to describe the target and the columns to describe the source. And so that the marble goes into position 0, since there is no cycle, it cannot come from 0. So it's a 0 probability. It can come from position 1, which is a 1/6 probability, or it comes from position 2, which is a 5/6 probability. This is the first row of our matrix, and I'm asking you now to send me the values of the second row of our matrix that would correspond to this system. So we would describe everything related to position 1. If you have the entries of the next row of our matrix, just send it and we'll compare. So we got a few answers, and they look great. So there's a 1/3 chance that it goes from 0 into 1. 50% chance it just stays, which is the cycle, or it comes from 2, which is the 1/6. So your answers are correct. And just to make sure all of you are correct, we'll do the last row, which then affects position 2. If you have any suggestions what these 3 values would look like, let me know. So since there's no cycle, the last element is a 0, because position 0 cannot get anything from position 2. And position 2 gets something with a 2/3 chance from position 0. And there's the 1/3 chance here. So that looks great. And again, we can use this mechanism to reflect dynamics. And we will now have our state X. And X is a probabilistic state of where the marble could be. we say it's a 1/6 chance to be in position 0, 1/6 to be in position 1, and a 2/3 chance to be in position 2. We see 1/6 and 1/6 is a third, plus 2/3 is 1. So it's a valid state. And now what I want to calculate is, again, m times x. So I have my transition matrix M, and from the right, I multiply my state, which was x, 1/6, 1/6, and 2/3. And with that, I can do my dynamics as before. And so I evolve my state by one time click into the future by using that dynamics. And if you deal with fractions, you can either do it without a calculator or with a calculator, but we can quickly try out what the result would be. So 0 times 1/6 is 0. Then we have 1/6, and 1/6 is 1/36. And 5/6 and 2/3 we multiply, and then we add these two products up. Concretely, our result would be 21/36. Feel free to double check this. And for the other two rows, we would have 9/36 and 6/36. And this will finally add up. So 21, 9, and 6 will add up to 36 divided by 36. So it's 1. So it's a valid state. So remember, this is probabilistic. We only have probabilities of where that one single marble could be, and our transitions are also probabilistic. And then if we evolve this by one time click, we would have those probabilities. And all the things we did before, like we can multiply the matrix with itself to have two time steps in one matrix, all of that can be done again as before. It's just now probabilistic and not deterministic anymore as before. Are you all okay with this mechanism? Maybe thumbs up. There's a question if the fractions could be simplified. Yeah, you could definitely do it if you want. I just left them with the same denominator, so it's easy to add them up. If you want to simplify them, feel free to do it. But sometimes we simplify here in this course, sometimes not, just to maybe have easy numbers we can easily compare or add up eventually. But later it will anyway become more complex when we use complex numbers, when we describe quantum systems, and then probably using a calculator is helpful. So there was a question that I should repeat what the vector x is. So vector x is something we also had before when we dealt with deterministic systems. There we said that's a state, and in the deterministic systems, a state meant how many marbles we have in each position. And now with probabilistic systems, we only deal with a single marble that is at some position, but we don't know exactly where it is. We only know probabilities of where the marble could be. And initially, we say there's the highest probability that it's in position 2, but we're not 100% certain. So we have also probabilities to denote this for the other positions, and it's just probabilities where that one single marble is. We don't know it exactly because it's probabilistic. But then given that we have these three possible positions where the marble could be with certain probabilities, we can move the marble around, but these transitions are also probabilistic because, for example, here and there, we have two outgoing edges from a position. And before we had for each position exactly one outgoing edge. Here we have multiple outgoing edges. So that again adds some probabilistic behavior. So we have a probabilistic behavior in terms of the position, plus we have then probabilistic dynamics, and we reflect all of this with probabilities. And so we multiply x from the right with m, and then we have done one time step reflecting these initially probabilistic positions plus the probabilistic dynamics. Is that fine for the one who asked the questions? So the one who asked the question, oh, so there's a yes. There's a question here, if it's, and the student says, maybe it's too early for the question, but how exactly are the states calculated at the beginning of a process in quantum computing? We're not in quantum computing yet. We're so far in probabilistic computing. But what you want to know is, how does the quantum program start? And depending on how you do it, you could just have, you could have this randomly or specifically distributed, but that depends on the input to the quantum program. So that's something we will see in a few weeks, how you can initialize it. But since we're not at quantum computing yet, it doesn't make much sense to discuss in detail how it's initialized. Here, I just randomly picked numbers or numbers from the book to have some initialization, some state, and then we evolve it to get something new. But all of this will be later today. We will do quantum systems. And once we have done them, we'll get closer to quantum computing to discuss this in detail. I'll go back to my slides and just wait a second. So that's what we just did on the iPad. We have M, which was our matrix, and multiplied by X. And we also have a few more theory points we need to consider. So I highlighted this before briefly when I said it orally. I said we have some requirement on this probability matrix. And in fact, if you add up the probabilities of the outgoing edges, that needs to add up to 1. And if you add up the probabilities of the incoming edges in a position, that too needs to add up to 1. And you can see this if you look at our matrix from before. The row 0 adds up to 1. The row 1 adds up to 1, and the last row adds up to 1. And the columns also add up. Each column adds up to 1. And there's a clear reason for this, because we deal with probabilities and we want to keep probabilities and not sort of unnormalized values. So a matrix needs to look that way, that each row adds up to 1 and each column adds up to 1. So this was not just chance. This is in fact a clear requirement. And such a matrix where all the rows and columns add up to 1, that is a so-called doubly stochastic matrix. And that's a term we will need later in this course again. So remember, a doubly stochastic matrix is a matrix where each row and each column adds up to 1. Then we can also, not sure if I'll show this. We'll do this on the iPad, I guess, then it's more interactive and I don't just need to show slides, and you can also try it out. Just switching back to the slides. And we had our matrix from before. I'll just write down the matrix again, because this time we will do something different with our matrix. So it was 0, 1/6, 5/6, 1/3, 1/2, 1/6, 2/3, 1/3, and 0. This is our matrix just as before. And so far, we had always multiplied a column vector from the right. So the column vector was this one here. Now we can do something else. We can use a row vector and multiply the row vector from the left. And we have some state, say it's 1/3, 0, and 2/3. This is this time a proper row vector, and we multiply it from the left. And we can also write this out and say, this is our matrix M, and we have our row vector W, and we multiply W from the left. Does any of you have an idea in terms of dynamics what this could mean if I'm not multiplying a column vector from the right, but I'm multiplying a row vector from the left? If you have any suggestion what could be happening, maybe just turn on your microphone or share this in the comments, what maybe could happen, because if we multiply a column vector from the right, we move one time click into the future. And if I multiply a row from the left, maybe we're doing something slightly different. Anyone has a suggestion what could be happening? If you have a suggestion, maybe raise your hand or green sticker. The one who raised the hand, feel free to turn on your microphone and tell us what you think could be happening. Hello?
Hello, can you hear me?
Yes.
Maybe we go one time step back, so we revert it.
Exactly. That's the right answer. We're not moving one time click into the future, but we're going one time step back. So if we sort of undo that operation, what the state looked before applying the operation. And that's exactly what's happening if we multiply the row from the left rather than a column from the right. And we can try this out, and we can calculate the first element. For example, we can say, well, it's 0 times 1/3, which is 0. It's 1/3 times 0, which is 0, and we have 2/3 times 2/3. So this would be 4/9. That's the first element. So we calculate now, for example, a row vector. Then we would be doing the same for this one here. So it's 1/3 times 1/6 and so forth. I'm not doing this in detail, but what we get is 5 divided by 18 and 5 divided by 18. And we see that's a proper probability vector, because 5 divided by 18 plus 5 divided by 18 plus 4 divided by 9, which would be 8 divided by 18, this would just add up to 1. So what we got here is the state one time click into the past. So we had applied the operation to something, and we got our state. And if I just want to undo the operation, so just go back one time click, then I know that's in fact the state I had. And that state as a column vector was used and multiplied from the right with the matrix to go one time step into the future. Then you get this. And if you want to undo it, use it as a row vector and multiply from the left. And you can just go back one time step. You probably wonder, what do we need this? The concept of undoing operations will be super important in quantum computing in a few weeks. Recently, last week, we talked about so-called unitary matrices. Maybe you remember that they are a concept, so we can undo operations. And the unitary matrices will soon be super important when we deal with quantum systems. But we're not there yet, so we're just starting to motivate the quantum systems by looking at probabilistic behavior, because quantum systems are, again, a generalization of probabilistic systems. But we'll get to them very soon. There is a little bit left on probabilistic systems that I want to discuss with you. So this is what I had just shown you, that we use our row vector and multiply from the left. So we're just going one time step back. You can also go back one time step by using the matrix M, and you're transposing it. So if you transpose the matrix, so we're just mirroring along or reflecting along the first diagonal. And if you look at our quantum system from before, we had the operations here 1/3 and 1/6. So 1/3, 1/6. And in fact, when we use the transpose, we're just flipping them. Feel free to transpose the system or the matrix in detail, but we're just flipping them, the 1/3 and the 1/6. So the directions of these angles, they are also just getting inverted if we transpose the matrix. And if we transpose the matrix, we will now have a matrix to also go back in time. And you can try this out from what we just did before, because before we had our row vector, which was 1/3, 0, and 2/3, which is a row vector, and we multiplied it from the left with our original matrix. Now we have transposed the matrix, and we have transposed our vector, because now it's a column vector, not a row vector anymore. And I'm multiplying the transposed matrix, and then from the right, I'm multiplying the transposed vector, and I'm also getting the same result that we just saw, 4/9, 5/18, and 5/18. So I'm also undoing something that way by using the transpose matrix. And I also need to transpose the vector, because I always multiply from the right a column vector. I only multiply row vectors from the left. So there's also a transpose here. And there is, if you're an expert in linear algebra, when you study linear algebra and you learn about all these foundations of transposing and rules of transposing, you learn something like, well, if you have M transpose and W transpose, that would be the same as if you multiply W and M. So you're just swapping them. As you remember, this is typically not commutative when you multiply matrices. So the order matters, but then you multiply W and M and you transpose. That's the same as M transpose and W transpose. And before, what we did was we used our W vector, row vector from the left with M, and that gave us a row vector. And if we transpose that row vector result, we in fact have our column vector again. So by taking advantage of this property of matrix transpose and multiplications, it means we multiply from the right, we go one time step into the future, so from t to t plus 1, whereas multiplying on the left, we go one time step back. And this is a time symmetry, because we can always do an operation and we can eventually undo it. And this will be a very important concept in quantum computing, which we will still see. But now it's motivated in terms of probabilistic systems. All the stuff we did in deterministic systems, like multiplying the matrix M with itself in order to do 2 time steps, you could also multiply it K many times with itself. It's exactly the same behavior as before for deterministic systems. Feel free to try this out at home. We have our matrix M, which represents our graph. We multiply M with itself. We get something like that, just in order to do 2 time clicks with one operation. But I'm not calculating this now step by step on the whiteboard. Feel free to double check this matrix at home. And the matrix that we get here also has to be doubly stochastic, by the way. So each of these transition matrices is double stochastic. Also, if you multiply it with itself, you still get a doubly stochastic matrix. There is a few more examples for probabilistic systems, but I'll give you a 10-minute break for now. So we will resume at 10 past 3, and then we look at a few more probabilistic systems, and then we advance to quantum ones. So see you in 10 minutes. Welcome back from the break. We will now discuss another example on the whiteboard. So, which is called the stochastic billiard game. And what it's about is we have 4 positions, 0, 1, 2, and 3. And we assume we have our 1 marble, and we can move it around. If it's in position 0, it will go with a half probability into position 1 or into position 3. If it's in position 1, it goes with a half probability into position 0 or into position 2. If it's in position 2, either goes into position 1 or 3, and so forth. So all these edges have a half probability. We can also describe this in terms of a matrix, which we call A. And by now, it should be fairly easy for you to come up with this matrix. Maybe you can try to describe in the chat what the first row of this matrix would be. So where the marble may come from in order to go into position 0. I'll wait for your responses in the chat. Since there's no cycle in 0, it cannot come from 0. It cannot come from 2. So only from, and I made a tiny mistake. I'm sorry, it's correct in the slides. I have to rename those because it then we could continue with the names I used, but we probably just do it as it's in the slides. So I just exchanged the 3 and 2 here. It's just the names, which would also lead to slightly different responses that I got from you, but I just want to use the same numbers as in the slides. Otherwise it will be confusing for revision, but there's just a minor change to your answers. So for position 0, it cannot come from 0 or 3. So we put a 0 here. And there's a half probability that it comes from 1 or 2. For our position 1, it can only come from position 0 or position 3 with a half probability. For position 2, it can only come from 0 or 3. And for the last row, for position 3, it can only come from position 1 or 2 with a half probability like this. So that's what our matrix will look like. And this describes an example that is called the stochastic billiard game in the literature. We use, again, doubly stochastic matrices. Each row and each column adds up to 1. And now we can try out something. We can use our matrix A, and we multiply it with a start state. And the start state would look like 1, 0, 0, 0. So that start state, which we can call X, for example, says we definitely have the marble in position 0. And now we multiply it with our matrix A. And if you know which state we will get now, if we multiply from the right our start state with the matrix, Send it to the chat once you know what the result would look like, and we can compare. So we get a 0 in the first and last element, and we get a half in these other two elements. So it means we have our marble in position 0, and then it either ends up in position 1 or 2 with a half probability. It cannot be in 0, it cannot be in 3. That looks simple. But now we will try again, one more time click. So we use A, and we multiply it with, so we call this Y, and now we use Y and multiply it from the right with A. So this was the Y we just had from over here. And I want you to multiply our vector Y from the right with A. So meaning we do one more time click. And I want to know from you which result you get if you multiply this. So we are doing one time step and then again one time step. And once you know what the vector would look like, send it to the chat, please. And the submissions are correct. It's 1/2, 0, 0, 1/2, which sort of makes sense because in the first time click, I'm in 0, and which is definite because of this 1. And then it's in position 1 or 2. And then I do one more time click, and then the marble is either in position 0 or 3. And that's why we have the 1/2 here and there. This is something that you should just remember for now. It's fairly easy in terms of the probabilities, but we will soon see a quantum version of this. And when we use quantum systems and we use complex numbers, then this billiard game will start to behave differently. And we will make some very strange observations because when we deal with quantum probabilities, all of this will behave somewhat different, but you'll see this later today. We will also have another example that I'll just check if I'll do this on the slides or here in on the iPad, probably on the slides, because these matrices would soon get very, very big. I'll share the slides again in a moment. Just wait. We will discuss now briefly the double slit experiment. Any one of you remembers the double slit experiment from, say, high school when you learned physics? If anyone has ever heard about the double slit experiment in quantum, maybe send a thumbs up or green sticker. And some of you have seen it, others have not. You don't need to know it, and we will now not look at the quantum double slit experiment. Rather, we will look at a simplified quantum slit experiment, which is the probabilistic one. And later, when we look into quantum systems, we'll look at the double slit experiment from a quantum perspective. What a double slit experiment looks like, you need to imagine you have a bullet. Later, when we look at the quantum one, we will deal with photons, but so far we're dealing not with tiny elements like a photon. For now, we will deal with a bullet. And we will have our machine gun here, and we have two holes, and we have a 50% chance to shoot into this hole here or into this hole there. And once it's at the hole, say in the top hole, it goes through, it either ends up in the first, second, or third target. It's just, a description. It obviously doesn't work as it's visualized. It's just a simplification. Or I shoot with a 50% chance into this slit, and then it ends up in the third, fourth, or fifth target. It's just bullets for now. It's not photons, as in the double slit experiment you may have seen in schools. And we'll also see the double slit experiment later today or in one of the following lectures when we deal with photons and we do the quantum one. We can describe this behavior in terms of a matrix. And the matrix will come in a second. First, we will describe all of this in terms of a graph. Just zoomed in, so the probabilities will be a bit more obvious. So we have position 0. This is where the machine gun is placed. And I shoot a bullet, which then would be one time click. We would be either here at the first slit or the second slit. So that would be one time click. That means I'm in position 0, and position 1 in the next time click would be the first slit or the second slit, which is position 2. There's a 50% chance I shoot to the first slit or the second slit. So I have a 50% chance here and a 50% chance there. Then if I shoot through the first hole or first slit, then the bullet will either go in target 1, 2, or 3, each with the same probability. So there's a 1/3 probability it goes from position 1 to 3. Position 3 would be the first target. There's a 1/3 probability it would go from 1 into 4, meaning the second target, or a 1/3 chance to go from 1 to 5, which is the next target. And then I have these cycles here, which are with probability 1. In case I want to do more time clicks, I'm in the target, I cannot evolve further. So that's why all of these cycles have probability 1. However, if I shoot through the second slit, which would be the position 2, there is a 30% chance, 33.3%, so 1/3 chance to go from the slit into this target, or this target. So 1/3 here, and again, also the cycles in the other positions. So position 5 would be the third target, 6 would be the next target, and 7 would be the last target. We can try to describe all of this in terms of our matrices. And this matrix is actually, it looks big, but it isn't that complex, because the first row is all 0, which sort of makes sense, because I can only leave from position 0, nothing is coming back. Then from position 0, we have a 50% chance to go into position 1 or 2. So this 1/2 up here would be for position 1. This would be for position 2. There is a 50% chance it's coming in from position 0 into 1 or the other. Then I have position 3, for which there is a third chance it's coming from position 1. There's the 1/3 chance it goes from 1 to 4 or from 1 to 5. So I have these 1/3s here. I have these cycles so that it stays in 3, 4, 5. So I have part of the diagonal here. And for position 2, there's this 1/3 chance it goes from 2 to 5. So this would be this one here, because this is the row that corresponds to position 5, but it has 2 edges coming in, one from 1, one from 2. So I have these 2 1/3s here, and I have these cycles and the last 2 rows. So this would describe our double slit experiment. Do you notice anything about this matrix which makes it sort of different to a property we had before required for our matrix? If you sort of see something looks strange about this matrix, maybe send a thumbs up or send a red sticker if you don't see anything, but maybe a thumbs up if you notice what could be wrong with this matrix compared to a property we had before. And we got a few good answers. The rows and columns, or the rows don't add up to 1. The columns, in fact, do. So the matrix is not doubly stochastic. it's just a simplified example. So we're not using properly doubly stochastic matrices, but it's just a simplified example because we will also later look at that again from a quantum perspective. Now, I said, if we do one time click from the start state, then after one time click, we are in position 1 or 2. And then one more time click, we are in one of those positions, which are the targets. And if I want to describe what happens after 2 time clicks, again, I can multiply B with itself, and I will get a matrix like this. Feel free to do the calculations at home to come up with this matrix, but here in the slides it is, and you can also find it in the book. If you enjoy doing matrix multiplications, feel free to do them, but you will get this matrix B squared. And if we have our matrix B squared, which represents the 2 time clicks, we can start with our start state, which is 1 and then all zeros. It's a column vector, but I just need to save space so it fits on one slide. So it's a row vector for now. And the 1 would be the start state, meaning in our experiment, I'm here and I'm starting to shoot the bullet. That's the start state where I haven't shot yet, but I'm about to shoot. So I'm in that position 0 in the machine gun. And then I do 2 time clicks. So I multiply B squared with X, and very importantly, X from the right, because I want to go time clicks into the future. And I'm doing 2 time clicks. And if I multiply this column vector with B squared, I will get this vector. Because if I do 2 time clicks, it's obvious I have to be in one of these positions, because the first time click gets me to one of them, and one more time click to here. And there is a 1/6 chance I'm in here or there. There is a 1/6 chance here or there, but there is a 2/6, so 1/3 chance I'm in position 5, because there are 2 ways I can get into position 5, either through the first slit or the second slit. And that's why I have a 1/3 here, which represents that position 5. Does that make sense to you when you look at the matrices and the start state? Maybe thumbs up if that looks okay, or if you have any questions, send them to the chat. Feel free to do these calculations in detail at home. And what we see here in this probabilistic double slit experiment is that these probabilities, they add up. So there are 2 ways to get into this third target, which is position 5, which is through one slit or the other slit. And this only works in our probabilistic double slit experiment. Now, very quickly, we're getting to quantum systems, and there we will deal with complex numbers, and something totally different will happen when we repeat the double slit experiment, not for bullets, but for tiny particles like a photon. So we will see this example again. We will see both the double slit experiment as well as the billiard game. Both of them will appear again today when we do quantum systems, and they will behave different. Now, we'll look into quantum systems, which is just another evolution of the mechanism we had studied so far for deterministic and probabilistic systems. We need something new. We need to work with complex numbers, and not anymore with real numbers, because so far we only worked with real numbers. And why do we actually need complex probabilities? When we use real probabilities, we can only add up probabilities, but probabilities with real numbers cannot cancel out because we don't have negative probabilities. So when we add up probabilities, they can only increase. And with complex numbers, we actually built a mechanism so they can cancel out. And we'll also do this interactively in the whiteboard. there's some bug with Zoom that sometimes when I do the screen share, that clicking these buttons is somehow frozen, and I always have this. So sometimes if you see my home screen on the iPad, it's not because I'm too slow, but it's just somehow frozen, or the focus doesn't work after I click the screen share, and it needs a moment. Imagine now we have two complex numbers. One is C1, which is 5 plus 3i, and we have a second complex number, which is -3 minus 2i. And please, for you, without looking at the slides, I want to know from you, what's the modulus squared of C1 and what's the modulus squared of C2? If you know this, send it to the chat. The modulus is the absolute value or length, whatever, of the complex number, which is given by these two bars. And if you square it, you have the modulus squared. If you have a suggestion for what that could be, so the first one, send it to the chat. If you have a suggestion what the second value could be, send it to the chat as well, please. This kind of notation that we need to square the modulus, since I haven't received an answer yet in the chat, I'll show it. So what you remember is, if I want, say, the modulus of C1, we said it's something like this: the square root of 5 squared plus 3 squared. So the square root of 30, let's do it step by step, 25 plus 9, so the square root of 34. That would be the modulus, but the modulus squared would be just squaring this, or just not taking the square root in the first place. So if we take our complex number C1 and take its modulus squared, it's 34. And for C2, this would be 9 squared plus 2 squared. Sorry, I'm too fast. Obviously not 9 squared. It's 9 plus 4. It's 13. So modulus squared. This is something you will actually be dealing with very often from now on when we deal with quantum computing, that we sometimes have the modulus and we need to square it for something that will become more obvious later. What we notice is, if I have my complex numbers, C1 and C2, and I take their modulus squared and I add up the modulus squared, the sum is greater than any, so 34 plus 13 squared gives me some number that is bigger than 34 or 13. It only goes up because these are positive values, or 0 at the best, but I cannot sort of subtract anything. And if I have complex numbers, say I have C1 and C2, and I add them up, then what I get is, I get 2 plus I, because 5 plus minus 3, which is 2, and 3i minus 2i is I. And now, if I take the modulus squared of this, then the modulus squared here would be 4 plus 1, which is 5. So what I can see here, this is actually, this 5 that I get is less than 34, and it's less than 13. So if I add up complex numbers, they exhibit something or a behavior that we also say these numbers or these probabilities, they can cancel out each other, because in the complex number, if I use complex numbers to represent probabilities, the real part and the imaginary part can be negative. And if I add them up, they have this behavior that they can cancel each other out. This is something we will later see when we deal with the double slit experiment, for example, and the effect that probabilities are able to cancel each other out is something that is fundamental to quantum computing, as we will see in the coming weeks. Sometimes that effect is also called interference, so that probabilities can cancel each other out. It's something we will also emphasize when we look in quantum or in quantum theory in detail. I'll quickly go back to the slides, a few more slides, and then again, some exercises. So this is just what I said, and we had done this example in the whiteboard. Interference is what I mentioned. And now we will deal with quantum states. Remember, our deterministic states were the number of marbles we have in each position. Then we dealt with probabilistic states where we had one marble and we said it's in one of those positions and we have probabilities. And these probabilities had to add up to 1. And now we will deal with quantum states. We will not anymore insist now in a quantum state that the sum of the entries need to be 1. That was a requirement for probabilistic states. So the probabilities need to add up to 1. In a quantum state, we have a different requirement. In a quantum state, we will now have complex probabilities, and the sum of the modulus squared of the entries need to add up to 1. Concretely, we have a quantum state now, also for a system that has 3 positions. We have a 1 divided by square root of 3 probability for the first position, a 2i divided by square root of 15 probability for the next position, and the square root of 2/5 is the next probability for position 2. And again, we deal always with column vectors. I just often have to use in the slide row vectors that I transpose. They just fits on the slide because otherwise I need a lot of space in the vertical. I'm asking you, is this a valid quantum state or not? If you think this could be a valid quantum state, maybe green sticker or red sticker if you don't think that this is a valid quantum state. Only one answer so far. Everyone thinks only red stickers. Anyone maybe more positive or wants to take some time to think maybe it could actually be a valid quantum state. Remember, the condition we have for a valid quantum state is that the sum of the modulus squared of the entries must be 1. And since there are doubts about this, we can try to calculate this now on the iPad. So the state we just had was something like the first probability is 1 divided by square root of 3. Next probability is 2i divided by square root of 15. And the last one is the square root of 2/5. Now I want to know what's the sum of the modulus squared of these 3 probabilities. We can call them for now like this would be element 1, or element 0, element 1, and element 2. And I want to know from you what's the modulus squared of element 0. So what's the modulus squared of 1 divided by square root of 3? If you have a suggestion, send it to the chat. And it's correct what we got in the chat. That's 1/3. So it's a very simple complex number, only with a real part. And remember how I calculate the absolute value. I take the real part squared plus the imaginary part squared, and I take the square root in order to get the modulus. But since I want the modulus squared, I have to square that square root, so the square root just disappears. So all I'm doing is I'm taking the real part squared. And the real part is 1 divided by the square root of 3. So 1 divided by the square root of 3 squared is just 1 divided by 3. Next one, element 1, I take the modulus squared. What do I get? If you have a suggestion, let us know. Remember, it's 2i divided by square root of 15. And this is, as we were told already in the chat by one of our participants, it's 4/15. Now, the last one is element 2 in the modulus squared. So it's 2. Let's see, there were some different results. I'm just checking. 2/5. So I want to know from you, does that add up to 1 or not? We have these 3 modulus squared. Does it add up to 1 or not? One student says no, the other one says yes. Let's try out. So we need base 15, or you can just type this in a calculator. 1/3 plus 4/15 plus 2/5. Now I'm getting more yeses, so that's correct. So our state here is a proper quantum state. And it's still a relatively simple one because we only have a real or an imaginary part. Later, they will actually start to look more complex. And these are you all okay now with quantum states? Maybe thumbs up if you're okay with this quantum state. I know all of this is difficult dealing with complex numbers all the time in linear algebra structures, but practice is key. And if you want to see many more examples and solutions, always take a look in the book. Has any one of you already had a look at that book, The Quantum Computing for Computer Scientists? If you have maybe like a green sticker or something, if you've had a look at the book, there are some, I definitely like the book. It's, I think, a really good book and makes the topic very accessible to computer science students. And as we before have worked with deterministic and then probabilistic systems, we can also deal with quantum systems now. We have quantum states, and as there are quantum states, we can also represent the dynamics in terms of complex numbers. There's just one example here that I'm taking from the book. This is, so we have our 3 positions, 0, 1, and 2, and we now need to represent the dynamics, and this is just an example. There are some constraints on what these probabilities would look like. We'll discuss this later. So we have a cycle in position 2 with a probability that is I. So only the imaginary part is 1. This is a complex number. Then we have a cycle in position 0 with probability 1 divided by square root of 2. There's a probability of our state or of our marble moving from 0 to 1 with probability minus I divided by square root of 2. We have also an edge that goes from 1 to 0. The probability is 1 divided by square root of 2. And we have a cycle in position 1, which is I divided by square root of 2. We can again represent this as a matrix. And a matrix is something we'll call U. And I'll start with the first row. So there's a cycle here, and in 0, so this would be the first entry. So it's 1 divided by the square root of 2. There's a probability that 0 gets something from 1, which is this one here, which is 1 divided by square root of 2. And there is no edge from 2 to 0, so that's 0. I want to know from you, what's the next row? There are 3 elements in the next row, which then would depict position 1. If you know the probabilities, which you can just read here from our graph, send them to the chat. So maybe let's start with the 0 in the end, because there's nothing going from position 2 to position 1. So that's also, again, a 0. There is this edge here. So from 0 into 1, this is minus I divided by the square root of 2. We have this cycle, which is I divided by square root of 2. And the last row will be fairly easy. It's just 0, 0. So we only have to cycle in 2, which is I. So, as you see, it's just the same mechanism as before, because initially we started with deterministic transitions, then with probabilistic transitions, and now we use quantum transitions, which we will do for the rest of this whole term in this course, because we will always deal with specific matrices that allow us to represent these quantum computations. And for that, we need to work with complex numbers, not with integers or real numbers, whatever, or probabilities. We use complex numbers. So step by step, we have evolved now from a very simple mechanism, and it got increasingly more complex. We can also do operations as before. So we said this is our state X, this is our matrix U. Obviously, we can multiply X with U from the right to represent one transition. It's complex numbers. It probably takes you a little bit to do this and make sure you have the right results. So we're skipping that, and I'll show you that directly in the slides. Feel free to double check these calculations and see if you're coming to the same result. And in fact, what it looks like is this one here. So this was our matrix U from before, our start state X. And if you multiply X from the right with U, you get this new vector Y. Maybe the last element is the simplest one, because I have these 2 zeros, so only the I matters. And then I have this square root of 2/5, and I multiply it with I, so it's square root of 2/5 divided, multiplied by I. The other 2 are a little bit more complex, but it's definitely doable. Feel free to do that and see if you're coming to the same result, and feel free to try it out. It isn't that difficult, and we get a new vector. And for our new vector, feel also free to double check at home if this is a valid quantum state. Remember, the sum of the modulus squared of the elements needs to add up to 1, which is the case here. And you will have a proper quantum state here because there's some constraint on our matrices. And we'll discuss that constraint in a second. It's just a little bit nasty to calculate and multiply these complex numbers, but we practiced complex numbers last week, so you should be familiar with them. And feel free to try this out. If you have an okay calculator, so I have my calculators from Casio. I'm not promoting Casio, but I have one that I bought a few years ago. It can also do complex numbers. If you're wondering if your calculator can do complex numbers, just check on the keyboard if there's an I, which is often in a little bit of bold printed. Have you checked something like this? Anyone has a calculator from Casio or a different vendor that offers complex numbers? Maybe thumbs up if you have noticed that you have this at home, or maybe a red sticker if you don't have this at home. Just check your calculator. But there are a few positive signs. I bought a new Casio calculator a few years ago, and it offers this. The old model I bought 20 years ago does not offer that, but the recent ones actually do this. But again, this is no promotion for Casio. There are many other suppliers, but I think the Casio calculators are just the most ones. One student writes, she has 2 Casio, but they don't have an I, so they don't have complex numbers. Yeah, the old ones don't, but now the ones that offer complex, they're also relatively cheap. Sometimes some calculators you have to sort of turn into the complex mode in the settings that they work. Or one student writes, you can use Wolfram Alpha. That's also something I feel more confident, or I'm faster using a keyboard on a calculator than typing this in Wolfram Alpha. I'm just faster, but everyone has a different preference. So maybe some of you want to use Wolfram Alpha, and you can do this as well. There is a requirement for our matrices that they are actually valid. And actually, the matrices we're using here, they have to be unitary. Anyone remembers what unitary matrices are? If you remember from last week, maybe thumbs up. If you don't remember what a unitary matrix is, maybe a red sticker. With there only being thumbs up, but not many, remember a unitary matrix. We'll quickly go back then just to make sure we're on the same page. A unitary matrix is this one here, where you have the U and you apply the dagger, which is the adjoint operation. And if you multiply a U dagger with U and U with U dagger, then this needs to lead to the identity matrix. And the adjoint operation is, as you remember, I transpose the matrix and I take the conjugate of every element. And the conjugate is just, I flip the sign of the imaginary part. And then I have my dagger operation or the adjoint operation. And if I apply this to my matrix and multiply it with the matrix from the right, or just the other way around from the left, and both leads to the identity matrix, then I have a unitary matrix. And last week, I also said the unitary matrices are super important because they allow us to undo computations. That's something we'll also deal more with in the coming weeks. Today, when we dealt with the probabilistic matrices, we already saw how we can undo. Undoing simply worked by transposing the matrix, because we dealt with probabilities in a doubly stochastic matrix. But today, or now, we're dealing with quantum systems. And that's why we require that actually our matrices are unitary, because the adjoint of my matrix, so the dagger, allows me to undo the operation. And if we have unitary matrices, there's actually a link to the doubly stochastic matrices. And we have this notation here, and this notation means I take my matrix U at a position ij, so at every possible position, and I take the absolute value or the modulus, and I square the modulus. Then I have a real value. So for example, we take this one here, this element, and the modulus squared of 1 divided by square root of 2 is just a half. And then I have this 1/2 here. And if I do this operation for every element in the matrix, meaning I take the element value and I take its modulus squared, this one here would also be easy. It's just a 1 in the imaginary part. And then the modulus squared is also obviously 1. Then I get this matrix. So I've calculated the modulus squared here for every element. And then I see my matrix is also doubly stochastic because I only have probabilities left. And if I use a unitary matrix and I convert it using the modulus squared element-wise, I will get a doubly stochastic matrix. And doubly stochastic matrices are great, as we've seen before when we dealt with probabilistic experiments. Now, this is something I'll better visualize on the iPad. So we do it step by step. So again, a greater discussion of this unitary property. And assuming, so unitary matrices, say I have some state V, which is my state of the quantum system, and it evolves by multiplying the state from the right with my unitary matrix U. So the system has evolved one time click back. So we can also write this is then t plus 1. It's one time click because this is my matrix and I have my state V. I have a new state now. And if I then multiply from the left U dagger with what I had here, so this is the dagger. So I had U times V, and I multiply from the left my U dagger with UV, then these two just cancel out because U is a unitary matrix, and we learned if I multiply from the left the U dagger with U, or U and U dagger and from the right, then this leads to the identity matrix. And here I have the identity matrix multiplied with V, and the identity matrix is neutral, so this would just be V. So I'm able to undo this. So here this would mean I go one time step back. So I go one forward and one back. So I'm finally at my initial time step T. In the slides, I wrote something like I3. This just meant for our, I'm assuming to use matrix U here from the slides, which is a 3 times 3 matrix. So I3 just means it's the identity matrix for 3 times 3. So I4 would be 4 times 4. And remember the identity matrix, it's all 0 except the first diagonal, which is 0. So we see now unitary matrices are really good because they allow us to undo operations, to go a time step back. And this is a super important property we need in detail when we do quantum computing in a few weeks. But right now we're still in quantum systems and quantum theory, yet this is a motivation why we actually need unitary matrices. Something like the identity matrix 3 could also be visualized. So I have my I3 this could be visualized like I have position 0, position 1, position 2, and I would just have a cycle in each of them with probability 1. So this would be a visualization of the identity matrix. And remember, the identity matrix I3 would just look something like this, and all the other values are 0. And here we just have a graph visualization of that matrix. What we can also try out now is we have our matrix U, and we can also try to visualize the U dagger, or first of all, write it down. I have limited space here, so I need to make a little bit of free space for us. So I have U, and U dagger would look obviously something like this. The real numbers don't change, so this is still 1 divided by square root of 2, or at least the real values in the diagonal. But then I also transpose, plus I take the conjugate of the imaginary part. So these two would just flip. Plus I do the conjugate. So this would be I divided by square root of 2. This would be the 1 divided by the square root of 2. Then I have this one here, which would be minus I square root of 2. I have these zeros, which don't change. And this one here only changes in terms of the conjugate. So it's minus I. So this would be the unitary or the adjoint of U. And we can also quickly go to the slides and look at that. So what we see here in the slides is just the U dagger, the adjoint of U, which we have just computed on the iPad. And you can also try to visualize it. So this one here would then be minus I instead of I. And here the arrows, the direction changes, as well as the imaginary value just gets inverted. But feel free to try this at home in case there are any doubts. Are you okay with up to here? Maybe thumbs up if you're fine with what we have done so far, or red sticker or a question if you're not. So far, we have just used the same mechanism as before, and we only plugged in complex numbers, and we have the requirement that we don't use now unitary matrices, not doubly stochastic ones, and the modulus squared of the elements summed up needs to be 1 so that we have a valid state. Good. Positive responses. If you remember our quantum or our probabilistic billiard game from before, there is also a quantum version of this. And I'm just quickly checking. Probably we'll also do it on the whiteboard so we can understand it better. Just switching back to the whiteboard. Frozen again. No. This quantum billiard game we can also visualize it as a graph. Maybe that's the first place. We have, again, all these arrows, edges, and we will soon put in the concrete values. Remember, we're now in the quantum world. So if we just put a value that looks like a real number, it's still a complex number, but that complex number only has a real part and not an imaginary part, but we're still dealing with complex numbers. And in quantum, we have the requirement that we use the modulus squared, and they need to add up to 1, and the matrix needs to be unitary. So even when you see now, one student just turned on his camera, you will be recorded, or her camera. Just ideally leave the camera off, otherwise you'll be part of the recording. So even if you see like a number now, like this 1 divided by the square root of 2, if you compare this to the probabilistic billiard game, it was 1 divided by 2, and now it's 1 divided by the square root of 2. Why is there suddenly a square root? Well, because we're dealing with complex numbers, even if it's just a real part, but the requirement is always, it needs to be unitary. If we convert unitary to doubly stochastic by taking the modulus squared of every element and so forth. And all of that only works if we have this 1 divided by square root of 2. So it's a valid complex number to make these matrices unitary. If you plug in 1 divided by 2, that's something you would do for the probabilistic game, but not for the quantum game. So this is very important. And often in this course, you will see some numbers, they look like real numbers, but in fact, they are complex numbers only with a real part. And then often you have in the denominator, not just a number, but the square root of something. And I'm just writing this out. So I'm putting here the probabilities. And they are from the book, so I didn't come up with them. And we can try to convert this to a matrix, which we call A. I'll ask you maybe to suggest the first row of our matrix A that represents this matrix. If, or to represent this graph. If you have a suggestion for the first row, just send it to the chat, please. Which is fairly easy. It's 2 zeros and 2 non-zero values. So the first and last element is 0 because there's no cycle in 0 and nothing comes from 3 to 0, but from 1 to 0. So this is the 1 divided by square root of 2, and from 2 to 0, which is 1 divided by square root of 2. And you can, so the suggestion we got in the chat is correct, and we can just continue with this. For position 1, we have an incoming edge from 0, as well as an incoming one from 3. Nothing from 1 and nothing from 2. So the first blue one I highlighted is the 1 divided by the square root of 2. And the other one is this one here, because it comes from position 3. It's 1 or minus 1 divided by the square root of 2. And then there are 2 zeros. If we do this for position 2, it has an incoming one from 0 and another incoming one from 3. So 1 divided by square root of 2 and 1 divided by square root of 2. And the zeros. And for 3, we again have 2 incoming ones from 1 and 2. From 2, it's the positive 1 divided, 1 divided by square root of 2, and from position 1, it's the negative 1. So the negative 1 is here, and the positive 1 is here, and we have the zeros. So this matrix represents our graph. It represents the quantum billiard game. And in fact, there is something we notice now. We have our matrix A, and it's in fact a unitary matrix. Feel free to double check it at home if it's unitary. So in order to check if it's unitary, you need to calculate its dagger, its adjoint, and then multiply it itself with the adjoint, once from right, once from the left. If both of that leads to the identity matrix, you have a unitary matrix, but this matrix here is unitary. I've also written it in the slides. And we will notice something now. So I have a start state, which is again 1, 0, 0, 0. So that means initially I am in position 0, and I multiply this now by A. And I want to know from you, what's the result? If you have the result, send it to the chat, please. So we can say again, X is sort of the start state, and we get Y, which is then one time click after. So I just multiply my X with A from the right. If you have a suggestion of which vector I would get, then send it to the chat. It's a fairly simple vector. We got a good answer. It's fairly easy to do this multiplication because I only have a 1 here. So 1 times 0 is 0. 1 times 1 divided by square root of 2 is just 1 divided by square root of 2. So is the same for the next element, and then 0. So that means if I start in position 0 and I do one time click, I'm with equal probability in position 1 or position 2. Doesn't look different to the probabilistic quantum game, only that we deal now with the square roots in the denominator, because these are complex probabilities. And if you remember our probabilistic billiard game from before, we did one more time click. So the first time click was from 0, then with equal probabilities in 1 and 2. And then we did one more time click, and then we were with equal probabilities in 0 and 3. That was the probabilistic quantum game we did. And now we can try this here. I have my matrix A. I multiply it with my Y, meaning 0, 1 divided by square root of 2, 1 divided by square root of 2, and 0. And I want to know from you, what's the result? So we have my Y, this one here, and I multiply it with A to do one more time step. If you have a suggestion of what's the result, which vector I will get, then send it to the chat. We got a suggestion. I'll wait if there are more suggestions of what we get. So all you have here to do the calculation is our Y, and you multiply it with A. Maybe some more of you want to send a suggestion, and we'll see if there's a consensus. I'll go ahead then. So we multiply, we got a lot of different suggestions now, in fact, from the chat. So I multiply my column vector with the first row. I have zeros that cancel each other out. So these zeros. And then I have a 1 divided by square root of 2 times 1 divided by square root of 2. That gives me a half. And if I do the same again, it gives me a half. So it's a half plus a half, which means it's actually 1. Then I can try to do this for the next row. So 0 times something is 0. I have zeros here and 0 there. So this gives me a 0. And the same happens for the next rows. If I multiply them with y, it all gives me zeros. If you got a different result, probably you got something wrong, but eventually all of this will cancel out and you just get a 0, or you can try to do the calculations again at home. So now I'm noticing something very strange with this quantum billiard game. I do one time click, and then I do one more time click, and actually my marble is back in the starting position. And this is completely different to what we did in the probabilistic quantum game, because in the probabilistic quantum game, we actually did 2 time clicks, and then the marble was either in 0 or 3. Now it's guaranteed to be back in 0, because I'm not dealing with real probabilities. I'm dealing with quantum probability, or with complex probabilities, and some of them are negative. And in fact, all of this will cancel out, and I will be back after 2 time clicks in position 0. And this is the concept of interference I mentioned before. And you can actually try this out for yourself at home. You can multiply A with itself. So A times A, which is A squared, and this will give you the identity matrix 4 times 4. So this matrix multiplied with itself will give us the identity matrix. And when you try this at home, always take the matrices from the slides in case I have any typo in here in the whiteboard in a live session, which sometimes unfortunately happens. But in the slides, we definitely have this quite stable, because they have been improved over multiple years. This is in fact the 3rd time I'm teaching the course. So there are probably only very little typo left in the slides, but obviously there may always be some typo left, despite numerous attempts to improve. So A times A will give us the identity matrix. And then if you multiply the vector X with the identity matrix, it stays X. So in this quantum billiard game, we are observing the concept of interference. So this can cancel out, and it's also explained here in the slides. We do one more experiment for today, which is the double slit experiment. We did a double slit experiment today already for the probabilistic, in the probabilistic setting, and we will now do it in the quantum setting. I will show you the key elements of that today. It's explained in much greater detail in the book. You will always see in this slide deck, there are also some attempted or some suggested further readings. You should always do the further readings and look up in the book. So this is a very advanced course. So the expectation is you're not first year students anymore. So the expectation is you do some further readings. And they are sometimes in the slide deck, and also here for that case, which means you should do some more readings about a double slit experiment in the course book. Now the double slit experiment in the quantum setting will not be about bullets anymore. We will actually use photons. So very tiny particles that exhibit quantum effects. And before, for the probabilistic one, we saw that for the third target, we actually had a higher chance that our bullet ends up there because it could go there through the first or the second slit. And this will actually now behave slightly different for our quantum double slit experiment. So we have not a gun anymore, but we use a torch. So we use photons, and we will have quantum behavior. There is also a graph for all of that. I did not come up with that graph and describe these probabilities. This is something that comes from the book. And there's a clear reason why these probabilities look this way, but aside from the actual probabilities, there's some stuff in common. So we have our position 0, then in one time click, we're in position 1 or 2. And then we have one more time click, and we have a position for each of these 5 targets. And once we are in one of these targets, we stay there because we have these probabilities of 1. And as we had before, the probabilities 1/2 and 1/2 to go from position 0 to either 1 or 2, it's now 1 divided by square root of 2, because we use complex numbers and the requirement is it all has to be unitary. We want to have valid quantum states. So the modulus squared is key to that. And that's why it's not 1 divided by 2, but 1 divided by the square root of 2. And then we have these other transition probabilities. Again, I didn't come up with that. It's from the book, and there are good reasons for all of this to look that way. But for now, we just assume that these probabilities are correct. We don't try to derive them, but we will soon see that this double slit experiment works different, because it's not anymore like 1 divided by 3. Now it's like -1 plus I divided by the square root of 6. And some variations in terms of the signs, that either the real part is positive or the imaginary part is positive or negative, whatever. We'll see this. And there are still 2 ways in this graph to get from 0 to 5. One case through the 1, which is the first slit, or through 2, which is the second slit. And from there, we have these transition probabilities. But soon we will see that some very strange effect, again, interference, will happen. And something will happen in particular to position 5. The graph we had just discussed can again be written in terms of a matrix. These are the probabilities to go from 0 to 1, and then from 1 or 2 to the other positions. We have these transition probabilities. You don't need to know them by heart. They're just from here before, and we have them now in this matrix. And we have part of the diagonal, because we said once we're in a target, we stay there for later time clicks. So we again have these 1s as we had them before in the probabilistic double slit experiment. And this is just the graph from before. I just printed it here once more, and you can see, for example, for position 4, the only incoming edge into position 4, so 0, 1, 2, 3, 4, is this one here. It's -1 minus I divided by 6. For position 7, there is 1 incoming edge, which comes from position 2, which is this one here, 1 minus I divided by the square root of 6. And the interesting part is here, position 5, because we have an incoming edge from position 1, which is 1 minus I divided by 6. And we have an incoming edge from position 2, which is -1 plus I divided by 6. So it's just the same mechanism as before, now with complex probabilities. There's one thing I have to say here. This matrix is not unitary, which if you try to look into it, it's definitely not unitary. Why is it not unitary? It's a simplified double slit experiment because the light could travel in, or the photon may travel in many other directions, and this would severely complicate this experiment. So it's a simplified double slit experiment, and that's why the matrix is not unitary. But it doesn't matter because we only want to observe one specific effect. We don't want to be able to reverse the experiment, so it doesn't need to be unitary for now. And it's clearly not unitary, as you can see, if we element-wise convert matrix P, or transition matrix from before, into element-wise into the modulo squared. We get this matrix here. We see the column here doesn't add up to 1. This column adds up to more than 1. Or sorry, the column is actually fine. I meant a row. So this row sums up, the first one sums up to 0, the next row to 1/2, here to more than 1. So this matrix is not doubly stochastic. And what we also notice is if we take our matrix P, so the one from before with the complex probabilities, and we square it, so we multiply P with itself, something very strange happens. And the strange part is actually this one here. That means, so P squared means I do 2 time steps into the future. And when I said that with the starting state, my photon is in position 0, and I do 2 time steps, and this 0 will eventually lead to some problem. That means my photon cannot end up in position 5 in 2 time clicks, even though it sort of looks possible. Like I have a position 0, and I do 1 time click, I'm in 1 or 2, and I do 1 more time click, I could be in 3, 4, 5, 6, or 7. But when I raise P squared, and I have a 0 in here, that means if I start in 0 and 2 time clicks, somehow I cannot end up in here. And that's something that was impossible in the probabilistic experiment because we dealt with real probabilities. Now we deal with complex probabilities. And in fact, those complex probabilities, they can cancel each other out. So that's interference. And we will now look at that, why this can happen. And I will do this on the iPad and show you why that's the case. I think just to make it completely clear for everyone, I will quickly copy this matrix. So this will take a short moment. So if you need to have a quick coffee break, whatever, feel free to grab your coffee now, because I just need to copy all of this, which will take a short moment. But should go fairly smooth. So just wait 2 minutes and then it's copied. Hope I don't copy any typos. And then I have zeros here. -1 plus I divided by the square root of 6. -1 minus I divided by the square root of 6. Then a 1 here. There's probably some typo so far. I'll try to fix it. I'll just check if it's okay. If you see a typo, obviously send a hint, because this is absolutely non-trivial to copy paste this now in short time. Because maybe a column is missing. Yeah, I think one column is missing. Should be 8 columns, yes. And I need to copy it so we actually see what will cause the interference. So this is my matrix P, which now seems to be copied okay. And I said I want P squared. And then I'm just sketching P squared now. Because I will not fully copy it, but there is I can also put indexes for the rows 0, 1, 2, 3, 4, 5, 6, 7, 8. And for 5, checking it. The big anomaly is in row 5, where this is a 0, and it shouldn't be 0, because that would mean if I do the 2 time clicks, I'm unable to end up in position 5 with my photon. And we can try to investigate how we end up in this 0. And it actually is a consequence of when I multiply this matrix with itself. When I want to have this element in row 5 and the 0th column, it would effectively happen if I multiply this with this and this with this. And we can try to write this out and see why this eventually leads to canceling. So I take 1 divided by the square root of 2, and I multiply it with 1 minus I divided by the square root of 6, plus I have the 1 divided by square root of 2 and multiply it with the minus 1 plus I divided by square root of 6. We can see what will happen now when we calculate this. It will lead concretely to 1 minus I divided by the square root of 12, because this is the square root of 2, square root of 6. And over here, I will then have plus minus 1 plus I divided by the square root of 12. And then I have a 1 and a minus 1 and a minus I and an I. And this will lead to 0. And that's the 0 in P squared at that one critical component or element in the 5th row, which would describe the 3rd target through which I have 2 ways to get, either through the 1st slit or the 2nd slit, which in the probabilistic experiment increased the probability to get there. But for the quantum one, it actually cancels out and leads to interference. So we see probabilities are now able to cancel each other out, which is something we don't know from classic probability theory. And it's a very important property in quantum computing that we will see later through this course to actually help us to speed up computations. And it's a very useful property because we need, in quantum computing, we need to create highly parallel or we do highly parallel computations by assessing every possible solution at the same time in our computing problem, but there are unnecessary ones, and those we want to be canceled out. And that's something we'll see in a few weeks. So you see there's a reason why we actually discussed today interference and quantum systems and canceling out. This double slit experiment is explained in greater detail in the book. Feel free to read it. We will not discuss the double slit experiment in a very in-depth way in terms of physics, because in this course, we apply quantum theory in order to do computations. We don't care too much about quantum physics and its details. We only sort of use quantum theory as a probability framework in order to do highly parallel computations. What we will from now on always talk about is a so-called superposition. And the superposition is, we have seen our states today, and we started with deterministic states. And in a deterministic state, we said, well, we have 6 marbles in the one position and 2 in the other. Later, with probabilistic states, we said the marble is in one state. We don't know, or sorry, the marble is in one position, but we don't know in which one, but exactly in one. But we use probabilities to describe this. And now we use superpositions in our quantum systems, and superpositions allow us to express something different. We will say that our particle is not just in one position with a certain probability, it's in all positions simultaneously with a certain so-called amplitude. And the amplitude is related to our complex number. So we're not just with our marble in one position with a certain probability, but in all positions at the same time in parallel with the amplitude. And that's what we call a superposition in quantum theory. And this will be a huge help when we do quantum computing, because we can assess, in the ideal case, all possible solutions to our computing problem at the same time. And that's why we can get, in some algorithms, even an exponential speed up, because we don't need to assess every possible solution simultaneously. Rather, we assess all possible solutions at the same time. And for that, the concept of superposition in quantum systems is super relevant. There are more contributors to uncertainty. So quantum computing is a highly probabilistic or uncertain thing. There are many reasons for that. We also do a so-called measurement at the end of our quantum experiment, because we need to measure eventually where the particle is exactly. But that is also probabilistic, because we have probabilities, complex probabilities for every position, and a measurement adds on top uncertainty. So if I do the same quantum experiment twice, I may get different results, because the measurement adds uncertainty as well, to find out where the particle is exactly, or in a computing perspective, what is actually the exact value of a qubit. Is it 0 or 1? Because a qubit is also a quantum system. Rather than a traditional bit, we are not either 0 or 1, but we are 0 and 1 at the same time with a certain amplitude. And when I measure, sometimes I get the 0, sometimes I get the 1 for the same experiment. If the amplitudes are distinct, then one will appear more often than the other. Nonetheless, I need to run that experiment multiple times, because it adds uncertainty. So the measurement is also a mechanism we will explore in detail in the coming weeks when we look into quantum theory. But as I said, the power behind quantum computing is superposition, because we can be in many different states at the same time in our algorithm and manipulate all of these possible solutions or assess them at the same time. And this would not be possible with a traditional computer, only with a quantum computer. But you cannot just say, well, quantum computers are better in general, because you need to write a quantum algorithm that takes advantage of quantum effects, and that's non-trivial. But we'll see quantum algorithms as well. For today, just a brief summary what we had done. We started with deterministic systems. We established our matrices and states as a mechanism to think in terms of discrete time steps. We applied this to probabilistic systems, and then we applied this to quantum systems. So step by step, we got a little bit more complex. Next week, Horst Kuhnhardt will do his introduction about the history of quantum computing and dissonance potentials. I will be back in 2 weeks in this class, and then we will continue how we can actually assemble systems. So far, we only looked at a single matrix, a single system, but actually in a quantum computer, we not just want to deal with one qubit, but we want to deal with many qubits, like we want to deal with many bits in a traditional computer. So I need a mechanism in order to assemble multiple systems, in order to build a composite system. And that's what we will study in the next lecture that I teach. That we have two matrices or two graphs, and we can compose them or assemble them into one big one. And that's something we'll need in quantum computing in order to be able to work with multiple qubits in the same operation. And that kind of assembling or composite can be described very well with our tensor product. The tensor product is something we also introduced last week. In my next lecture, you'll see what it's actually useful for. And then we are also done with systems, and we can dive deeper into quantum theory. Once we have discussed the quantum theory, we can use it to build fundamental computing units, and then we go deep into quantum computing. Are there any questions from your side? If you're all good, maybe just thumbs up. If there's doubts or questions, maybe send a red sticker, then I'll wait for you to send your question. But with there being no red stickers, we are done for today. I know it's tough today. You need time for revision and further readings. Also in the book, you should look into the double slit experiment a little bit more and read up about systems. Next week, we'll use the same Zoom channel, and Horst Kuhnhardt will teach the lecture. I'll just join in the very beginning to make him host and start the recording, and I'll continue the teaching in 2 weeks. So make sure you repeat and revise what we have done today, because you'll definitely need it next time. There's a hand raised. What's your question?
Yes, I have a question about the book. Is it possible to find it in some bookstore in Deggendorf, or we should look for it in internet only?
Obviously, you can order it from a bookstore, which is for which you need to pay. If you take a look at my Nextcloud course, there's a resources directory in the quantum computing course. And I've uploaded a PDF there, so you're able to find it there if you need a PDF. Here in a university, in a limited access setting, we're allowed to share such PDFs, even though they shouldn't be shared fully in public. All right, with there not being any further questions, we're done. I'll see you briefly next week, and then after Professor Kuhnhardt's lecture, I'll see you in detail in 2 weeks again. Take care, bye-bye.